students too, I suggested several topics to Vladimir Chisik, but I think because of my age, he assumed that I was the best to speak about the antiquities. So I have chosen two topics, the Egyptian pyramids and the Maya blue. So this is the first pyramid. It has been built by the architect Imhotep during the time of the pharaoh Djoser, around 2630 before Christ. And it is the first one in the part we call Sahara. It is the architect there. You can, if you visit Paris and the Louvre, the museum, you will see his statue. Imhotep was not only an architect, he was a genius man. He was the number 2 in Egypt. That means just below the pharaoh. We could say today the prime minister, if you prefer. And he was not only an architect, he was a chemist, he was a physicist, he was a believable man. Okay. So, but the colors are not very beautiful. You cannot arrange this? The colors are not very beautiful. A little bit stronger, no? Because for the Maya blue, it will not be beautiful. Okay, no? So it is at this, okay, this is the map of Egypt, okay, near the river, the Nile. And the yellow triangle are the limestone quarries. In fact, it is there that you find the silica alumina near the country. And the first pyramid is there. Okay? The second pyramid, also with the plan of Imhotep, is a Darshur pyramid. The shape is completely different. In fact, it was not very stable, and this is why the picture looks like this, because it more or less cancelled. But when we speak about the pyramids, we think, of course, about the Giza, or Giza, depending on the pronunciation, of the pyramid in Egypt, and especially, of course, the biggest one, the pyramid of Cheops. Which has been built at this time during 20 years, approximately 20 years. It contains about 2.5 million of blocks. And the base is a perfect square. In that time, the difference between the longest and the smallest side is lower than ½ meter. In average, people assume that each ton, the weight of each ton is about 2.5 tons, but they are also much bigger. And for example, the ceiling of the tomb of Cheops is estimated to be 60 tons. And of course, you know, there is in the literature a lot of hypotheses how it was possible for the Egyptian, first, to make so many block in 20 years, because if you do the calculation, you will see that it's necessary to have a new block each minute. Okay, there were a lot of slaves and so on. And in addition, they did not know the wheel. You know, the wheel to bring up the stone. And in addition, they had only copper. Okay, people assume that at this time there was also the edge of bronze. But they don't have tin. So they have to import tin, and I don't think if they import tin, it will be for making 1,000 and 1,000 chisels. So this is a question for a lot of people. We'll not solve today the problem. Okay, so Giza is there. The first pyramid is there. The second pyramid is there. After you had a lot of small pyramids there. there you have the limestone, the site where you can find copper. There you have a lot of metals, but in fact you don't find this metal, or very rarely, near the river there. I come back to this pyramid. I told you where it is located, there. And now we look at, I have to remind you, when you have a silica alumina, for example, a zeolite, but also amorphous, you have silicon, oxygen 4, surrounded by silicon, or silicon and aluminium. And so depending on the number of aluminium, you have 5 different signals. And this part there corresponds roughly to silicon surrounded by only silicon, and it is at about 110, 120 ppm with respect to the reference. You see that we have large variation, but the large variation depends only on the structure. It depends on the distortion of the tetrahedra. But for the same compound, of course, you have a specific, of course, line. It is the same for the aluminium, alumina, sorry. You have there aluminium oxygen 4 at about 60, 70 ppm with respect to the reference, which is there, corresponding to the aluminium oxygen 6. This is very rare. We don't take care today. So now we look at the silicon and aluminium NMR of the pyramid stone of Darshur. This is this one. For silicon, this part corresponds to the silicon surrounded by 4 oxygen. For silicon, of course, for the oxygen. Okay. And you can look at the spectra, the NMR spectra of silicon, for all the limestone quarries you can find near the river. They are all very bad. For example, the best is this one. And this one is a limestone quarry near Tura. I will show you later. All the others are like this, for example. That means very far from the spectrum of the stone of the pyramid. It is the same there. For the aluminium, you have there the signal of aluminium oxygen 6. And you see that they are all, these two, for example, are very bad. And you see that this is the signal of the pyramid and the signal of Tura quarry. And you have there the small deformation characteristic of this limestone. So there is no doubt at all. For the Darshur pyramid, they use the limestone quarries of Tura. Where is it? This is a calcium NMR, but we don't get any information about the calcium. So where is it? The pyramid is there, and Tura is there. The distance is about 60 kilometers. 60 kilometers, 2,060 years, 600 years before Christ. It's not the next door. In addition, they have to cross the river. Rather difficult. I have to introduce, but really the pictures are not beautiful. Huh? Okay. I have to introduce now a man, is a Professor Davidovits. Professor Davidovits has two, is a French, long time ago, maybe after Napoleon or after, I don't know. Okay, and Davidovits is a professor, is a chemist, not only a wonderful chemist, but also one of the best men knowing the Egypt, antique Egypt. Two possibilities, two knowledge. And it is the father of what we call the geopolymerization. The geopolymerization is exactly the same as the polymerization you know, but you know the organic polymerization. That means only with carbon and hydrogen, and of course some additional atoms from time to time. And this one concern only the polymerization with inorganic compound, and mainly silica alumina and different some other atoms like iron, phosphorus, and so on. So he has built a completely new chemistry of inorganic chemistry. And is very famous. And you see, for example, if you build a house everywhere in the world, even if the cement has not the same name, it is what we call the Portland cement. Maybe the name is different in Russia, in the States, in France, and so on, but it is exactly the same composition. And the synthesis is not difficult, but it's more or less complex, and it's rather expensive. And this man has been able to build, to do the synthesis of a new cement, lighter. The synthesis is easier and much less expensive, and stronger than the Portland cement. And it is so famous that you see the variation of the paper from the first publication of this man, and in 2013 there were 400 papers a year on this chemistry. And it is so important that the Canadian people want to build a very big new airport, and they will use totally this cement for building the airport. So it's only to precise that this man is really a wonderful chemist. But he is also a wonderful specialist of Egypt. So he has been able to make this chemical reaction, which is very easy, of course. That means the sodium carbonate with lime, you obtain the soda and calcite, and you can use this soda to react with the clay to form this compound there. And this compound is really a binder for making the cement and the stone very strong. Okay, but it is in the laboratory. And if we look at the NMR of this binder, this is the aluminium, specific the signal of the aluminium. Of course, this is the other part of silica. And this is the silicon. And you remember we had, when we compare the two spectra of the pyramid and the Tura spectrum, we have seen we had a deficit of this powder. Remember? Near 111 ppm. Okay. And so the idea of this man is to do the analysis of the stone by NMR and to see that this is a binder done in the laboratory, and this is, for example, the Cheops, but it could be also the Darshur stone. And the stone of Cheops contains 15% of this binder. Where is it? We don't find this chemical compound everywhere in Egypt. It does not exist. How is it possible? It's possible because the Egyptians had the full material to make this binder. They had the sodium carbonate in Egypt, they call the Egyptian natron, but it's this carbonate. They have the lime, so they can make the soda, and they react with the silica alumina of the quarry, and they obtain this compound. What it means? It means that the stone of the Egypt are, not all of them, but partly synthetic. That means Imhotep was able to do geopolymerization 2,600 years before Christ. Okay, but are there some other proof? You see, this is the stone of Cheops. It is perfectly smooth. You have no trace of Giza at all. And Davidovich has been able to build exactly similar stone of Cheops, exactly the same. This is the Cheops, similar of Cheops, inside the pyramid. And this is a stone near the edges of the pyramid. They are totally artificial, made in Saint-Quentin, not far from Paris. They are similar, totally similar to some stone of the Cheops pyramid. Okay, maybe it's a dream. This is Giza Plateau, where you have the biggest pyramid. And in fact, you have 3 layers. You have 2 layers of very hard gray limestone there, and this is very soft. And it is this soft silica alumina that they have used to make Cheops. But they cannot use this material like this, because if you put in water, it is totally disaggregated. And if you look at the Sphinx there, the head of the Sphinx has been done with a hard gray. And if you look at, if you visit, or maybe you have done it, if you visit this part, you will see that it is roughly like it was when they built it. But the body and the support, you see that it starts really to be disaggregated. But since it doesn't rain very often in this country, we have time, of course, to look at it again. Okay. So are there some other proofs? First, look at, I'm sorry if the colors are not really beautiful. It is a projector which is there. Okay. You see this stone. And you see the distance between the 2 adjacent stones is rather large and not very well done. This stone had been carved with a chisel. And the surfaces are not really soft. And you see immediately there, and especially there, that the distance between 2 adjacent is really, you cannot do it with a chisel. It's impossible. This doesn't mean that all are synthetic. No, you have seen that you have both, but many are synthetic. Another thing, this is a very big stone. This stone has been built to talk about the Stele of Famine. During, you know, the agriculture of Egypt is mainly coming from the Nile. For a given time of the year, the flow of the river is very strong, and the water overflows outside the river, and so you have the irrigation of the country, and you have the agriculture, and you have the food. But when the flow of the river is very low, you don't have such overflowing, and so you don't have food. And you had, during several years, people dying because they didn't have food at all. And it is a story in this stone. Some beautiful painting. Of course, you are able to read it yourself. Don't. Okay. And people did not pay attention to a lot of hieroglyphs, a lot of signs, not connected with the history itself of the famine. But now they paid attention, and they have seen that it is written on the stone that the stone has been made according to a recipe of Imhotep. For example, this is one of your hieroglyphs, and you have the eyes above the body there. This means that to work, to shape, to form, to do something. And these 2 arms above the sphere there means that it is created by man. Of course, if you are a specialist of the hieroglyph. This is another proof. You have in the Louvre, the museum in Paris, you have the Stele of Artisan, a very big stone with a lot of speaking about the history of this man, 2000 before Christ. And it is written on the stone that it is made according to the Imhotep recipe. You have even the picture. So what they do is they had something like a big swimming pool. They put the silica alumina in water, it is totally disaggregated. You have a very fine powder. So you can do the chemistry with this. And so they did the chemistry, and they put in some sign there. The raw material is there, and they bring up man by man to the site where the stone has to be done. They did not have to bring 1 ton, 2 tons, 3 tons. You have an army of slaves bringing little by little the material. So, of course, this is a model. It's not a... And another proof, if you look at in the quarry, the material is more or less crystallized. And in the pyramid, in a lot of stone, it is amorphous. This means that it has been mixed. Another thing, some million of years, this part was a sea. And so, normally, the fossils were more or less all in the same direction. And in the pyramid, they are distributed at random. Finally, if you want to read something about this story, you have a lot of data. You have also some proof with electron microscopy and so on. But I don't want to spend too time on this part because I want to speak also on the other part. But this man, you should know it, of course, the famous chemist, French chemist, studied this big statue, which is also in the Louvre in France, a very big statue. And he was the first to say that this statue was not carved but casted. But he was not able to prove because the Louvre did not give permission to take some part to prove it. Okay, and they have found in the different pyramids, and for example in Sahara, a lot of potteries which has been molded, and the man speaking after me will speak about these potteries later. Okay. I was not involved at all in the first part concerning the Egyptian pyramid. But I am totally involved in the second part, which concerns the Maya blue. Okay, I will not speak about the pyramid again, don't worry. But it's very surprising that at the same time, roughly 2,600 years before Christ, at two opposite parts of the world, in Egypt and in the Maya part, that means today the Mexico country, they built pyramid in the honor of the god or of the big chief of the country. Okay, but I don't speak about the pyramid, I speak about the Maya people, and the Maya empire was unbelievable. Maybe bigger than Russia today. No, it's not a joke. It is a half part of Mexico country today. It depends at what time. Okay, a large part of the half part of Mexico country. And it contains the Belize, Guatemala, roughly the full Honduras, a part of the El Salvador that you know today. A very big surface area. And nobody is able to understand why civilization, starting around 2,600 years, disappear roughly totally after 500 after Christ, and totally after 1,000 there is no more Maya at all. Okay, nobody is able to explain how these people die. Okay, and now if you have the chance to visit the part of Mexico country today, which is called the Yucatan. Maybe if you don't think about Yucatan, maybe you think about Cancun. This is a famous swimming pool, beach, and so on. Okay, so on. And you find on the wall outside, on some part in the city or in the country, you find some frescoes on the wall outside. 2,000 years ago, they were being painted, and they are again blue, like this. Another one, depending, of course, on the concentration of the blue. This is also soldier. This is also, I'm sorry, the projection is not good. Okay, this was inside a building, but despite of this, it is also very old. This is a statue which was for centuries and centuries in the forest. Now it is in the museum. They built in Mexico City, they built a new big museum speaking about the full history of the country. And so it is in the museum. This one is fantastic. It was also outside for a long time. Okay. Okay, normally you should see some blue. Okay, and what is this blue? Okay, people know what it is. They took, of course, a small part of the, and they do the analysis, and it is the addition of palygorskite. Palygorskite is a clay you find in the Yucatan. And indigo. And indigo, you know it. If you have a blue jean, you have indigo on your leg. It is very much used in the industry today and so on. What is it? It is this molecule. Don't forget the structure. Okay, and the palygorskite is a clay with a micropores. So this is a crystallite, for example. And so why I'm involved in such a study? Because I have proposed, maybe 30 years ago, I don't know if you heard about this, the xenon NMR technique, which is one of the best for determining if you have some pores, to determine the microporosity and to study the micropore structure and so on, especially originally it was for zeolite. Okay. And so they asked me, can you tell me, because they don't know, can you tell me if the indigo is on the external surface of the crystallite, or if it is in the groove, that means the defect near the surface, or if it is inside the channel? Okay, there in green, you have 4 aluminium surrounded by, we will see another figure later, surrounded by 6 red oxygen, and the oxygen bonded to silicon in rose there. Okay, 4 silicon, oxygen 4 there, and 4 aluminium, oxygen 6 there. Okay. We discover, not me, before, we discover the synthesis of the Maya. The synthesis of the Maya is the following. They put a plant, the Latin word is this one, let's say annual. They put it in connection in water, in contact with a palygorskite. We know this. And so for everybody, you have maybe 20, 30 papers published and so on. For everybody, the plant desorbs indigo, and indigo is adsorbed on the palygorskite. They forgot one thing, that the indigo is not soluble in water, but okay. So the question is where the indigo is situated. So I show you again. It can be on the external surface. It can be on the small defect near the surface or in the channel. So what we did with my Mexican team, I could say friends better. So we have done the synthesis according to the Maya preparation. We have been able to find the plant. It's not easy, but have been able to find the plant. Palygorskite you can find easily, it's not a problem. Okay, according to the Maya synthesis. And we dry at 180 C degrees, and the solid is rather white. Maybe bluish, but really nothing. And we did a synthetic preparation. That means we have bought indigo, and we mixed palygorskite with indigo, either in the solid state or dissolved in the MSO, because I told you it's not soluble in water. And we dry at 180 degrees. And of course, it is blue. We put indigo, it is blue. Okay. And we put this material, these samples, in this apparatus, what we call the accelerated weathering tester. That means in such apparatus, you can reproduce the weather as long as you want. So what is the weather in such country? Very hot during the day with UV radiation and very humid. And at night, it is more or less the same, less the UV radiation. So we left this sample during 200 days. 200 days means that it is equivalent to about 10 years outside. So we call the sample A after the treatment and F before the treatment. And we have done silica, aluminium, carbon-13, and xenon NMR. So just a few words about the concentration. These are the fresh sample according to the Maya preparation in green and synthetic in red. Okay, they have roughly the same concentration, except that for the Maya preparation, we have two different concentrations. And this is polygorskite. This is the fresh, and this is after the treatment. Of course, the concentrations are the same. So this is another picture of the structure. So the problem is to know if we can put there, taking out these two water molecules, is like a zeolitic molecule you can take out there easily. Okay, so you have in red aluminium surrounded by 6 oxygen. Normally you have 2 oxygen there. You don't know why they don't. Okay? And this is in black silicon surrounded by 4 oxygen. So you see that you must have 2 silicon peaks because these 2 and these 2 are different. But there the environment of the aluminum is roughly the same. So in fact you have only one light. This is a polygorskite NMR signal. Okay, a few words about xenon. Xenon, you can determine, you can absorb xenon. It's a rare gas. And it has several isotopes, and especially the 129, half spin, easily detectable. And so you can absorb it in the zeolite, for example. Originally it was for a zeolite. And you plot the chemical shift of adsorbed xenon against the concentration per gram of solid. And this is, you see, you have the variation for a lot of micropore structure. Okay, the increase of the chemical shift corresponds to the increase of the xenon-xenon collision. And because of the xenon-xenon collision, you increase the deformation and the chemical shift. And at the origin, it's more complicated. It depends on the interaction between xenon and the wall, but also depends on the ease of diffusion of xenon inside the crystallite. For example, if you have the same structure there, this one and this one, but the openings are totally different, you see the chemical shift is different because there the diffusion is less fast than this one. So what's the interest of this? The interest of this is now if you have polygorskite with indigo, and if indigo is inside the pore, you will change the number of free pores for xenon, but you will not change the structure of the residual pore. So normally you should increase the slope, but not change the position at zero concentration. So,
where is free xenon?
oh, but outside, but it's
in the free volume.
Inside the crystallite.
No.
It is adsorbed.
Yes, I see.
Yeah.
But there is chemical shifts free xenon.
Well, but it is. No, you cannot. The sensitivity is not high enough to detect the. At this pressure, you don't detect the gas phase. Okay, so this is a chemical shift of xenon against the concentration of atoms adsorbed in the fresh sample. That means before the aging. So this is the palygorskite. This is two samples according to the Maya preparation and the two synthetic preparation. They are more or less roughly the same. If you want, there are some errors. This is 2 ppm of difference there. The slope is a little bit different because the concentration of water is not exactly the same. Okay, but they are similar. So now if you look at after aging, after aging, you see that there you have the palygorskite alone, and you have the two synthetic samples. No change at all. That means the indigo is not inside the pore, and even is not at the entrance of the pore, because it could be at the entrance of the pore, blocking the absorption of xenon. So it should be in the grove and something like this. And you see that depending on the concentration of indigo with the Maya preparation, you increase the slope. The chemical shift doesn't change. This is the same. Okay, this means that some pores are blocked to the xenon absorption. Some others are totally free and similar to the beginning of the preparation. But this doesn't mean, not because you have such results, this doesn't mean that indigo is inside the pore, because indigo can be at the entrance and block the absorption of xenon. So it's a survey to look at if you have some interaction of indigo inside the pore with the wall of the pore. So if you to take out this water there, and you put indigo there. So if you put indigo there, you should have some interaction between the indigo and the oxygen surrounding the silicon there. Okay, the interaction should be not very strong, and so the perturbation of silicon not very important, but at least you should detect a change of the chemical shift of silicon. Now, if you put indigo there, you have the aluminium there. Okay, this is a very strong water molecule connected there, oxygen there. That means that, in fact, I told you the aluminium are roughly the same. So surely you will not change the environment of the aluminium. But you know that if you have a quadrupolar nucleus, it is very sensitive to the symmetry of the environment. And in that case, you will change slightly the environment of the aluminium, if indigo is inside. So this is a fresh preparation, palygorskite alone, and all the sample before the heating treatment. Nothing changed there. And for the aluminium, only the Maya preparation with high concentration, you see that you have widening of the signal, proving that the aluminium environment has changed a little bit. This is the two signals of the silicon, palygorskite alone, and for all the samples, you see you have a similar spectrum. For the sample after hedging, only the high concentration of indigo, you see, you have a chemical shift of the silicon. Of course, the chemical shift is not very important because it is through the interaction with the oxygen sample. So indigo is inside. But we don't understand. Maya did the preparation. The plant, in theory, dissolved indigo. So indigo should be absorbed on the polygorsite. And we see that indigo is inside after aging. And if we put directly the indigo on the polygorsite, nothing happens. Something should be wrong somewhere. And so we started the carbon-13 NMR, despite, of course, the concentration of carbon is very low. So this is carbon-13 of the first, the fresh and the edge synthetic preparation of one of the two samples. It's not sorry to do the same. This is the spectrum of the Maya preparation after aging. You see that they are really the same. We have indigo inside. So we did the carbon-13 of Maya preparation before aging. It has nothing to do with the carbon-13 of indigo. This spectrum is a spectrum of endoxyle, which is a small molecule soluble in water, and we can diffuse easily inside the pore. Yeah, but endoxyle is not indigo. No, but if you put two endoxyle inside the pore, under the UV radiation and the heating, you form the indigo. Okay, what it means? It means that 2,600 years before Christ, the Maya people knew the desorption, knew the aqueous solution, knew the adsorption, knew the diffusion in the pores, and knew heterogeneous catalytic reaction. You are really sure we are much better today? So I have to thank a lot of people. Of course, my old friends, due to my age.
Very good company.
And the architect, of course, and a lot of, you have there a lot of, I gave only some reference, but you have a lot of paper proving that, I repeat, we cannot say that all stone are synthetic, but a lot are synthetic. And I have to thank my Mexican colleague from the University, Central University of Mexico City. I thank you for your attention.
So thank you, Jacques, for the wonderful talk. And in the interest of time, maybe we'll limit ourselves to one question.
Oh, yes, sorry. Sorry.
Thank you. I try to formulate. Where ancient Egypt gained the soda and natrium CO3, and where did Maya get from where they gained endoxyle? From the plants?
Oh, there are two civilizations at the extreme,
yes.
at the extreme part of the world.
Yes.
But the Maya, maybe I don't understand the question. They did by hand.
Where they find, where in nature perhaps they found endoxyle to carry the synthesis.
No, but you have along the river, you have a lot of limestone quarries, and only few are useful for building. But despite they are useful for building, they are not strong enough to be all curved like this. They need also some binder. And for the Maya, it's very easy. On their country, they have polygon sky. You can find today, even if you go, you can find it. And they had some special plant. The plant is more difficult to find it today. And they put in water and they do it.
And,
but you know, it's not only the Maya.
Discussion, not question.
It's not only the Maya. If you visit, for example, near Mexico City, you have the Aztec civilization, another one. And you see a lot of frescoes in red. And they did, but they are younger than Maya. But they did the same with the plant, giving some red color by hand.
Wonderful.
Only.
Wonderful.
Oh, today, the painter is able to do his paint. Okay? And they were able to do their paint themselves.
Yes, it's wonderful. Thank you.
Okay, so now in view of the next question, Vladimir Ivanovich would like to make a joke, so please don't commit to laugh.
Jack, what?
I want to precise that despite of my age, I was not born at that time.
What is the dimensions of pyramid?
The square.
What's the about 150?
Yes.
Yes. About.
Yes, maybe, yes.
Maybe.
I know the head is 150.
The biggest. Yes.
It is the biggest, yes.
So the volume of one pyramid is 1/3 and 1/3. Yes. That's about 1/10 in the degree 6. And, yes, sorry. About. I think so.
So maybe the base is bigger.
You know that there are 3 pyramids. Yes. So.
No, but they have been built as different types.
Yes, but I.
Okay. Okay. Continue. Sorry.
These 3 meters cube, and then let's create a fence. A fence with thickness about 1 meter.
What is this?
1 meter thickness, and the height 3 meters.
What it is? A swimming pool?
Fence. This fence from stones
okay, yeah.
of pyramid.
Yeah.
So we have 3 fence in. Oh no. No. Here 1, 2, 3.
Okay, approximately.
Sorry. 3. About.
So the pyramid has collapsed.
This is approximately 3. 7.
We are saved, yes, okay.
No. 6. 8.
So you see, you are not able to build the pyramid.
1 and 2. Yes, 3. Yes. 6. About so.
Okay,
And
so.
For example, 2 meters.
Yeah.
The fence.
Yeah.
Fence.
Yeah.
And then 3. We divide on 3 times. So it will be about
1 million.
1,000 kilometers. Yes. The length of the.
Why? 10.6.
Yes.
divisé par 3, c'est 10.6.
Oh, why 3?
No, kilometers. Here
Okay, kilometer, yes, okay. Okay. yes, kilometer.
Why?
No, it's a kilometer, okay.
Kilometer.
Divide by 10, yes.
But,
Yes.
No. 1 multiplied on 2. 1.
Okay. So
This is S square of this space is about this. No. And we divide. Sorry. What are you doing? This is the land. Yes. Yes. So we have about this land is about
he is not Imhotep. And you stopped the question for me for this?
Yes. Sorry.
No, it's a joke. It's a joke.
This is square is approximately like Germany or France. Or France.
It better be France.
Approximately. So it's possible to create a fence which will be around France or
with
Germany,
a pyramid.
approximately.
With a pyramid.
From
Yes.
of 3 pyramids.
Yes.
No,
So,
you should tell this to Mr. Trump.
Sorry?
To build the fence.
but
It's rough.
Vladimir, I think that after the last election, I think we will need it in France. Okay.
Excuse me.
Let's be serious.
Okay, thanks very much once again.